the artificial neural net, as you can see in the title, is from the perceptron to multi-layer perceptron. So in my lectures, ANN, it's the same as multi-layer perceptron. So I want to explain the artificial neural net from the perceptron. I want to develop the concept to multi-layer the perceptron. Let's see. So as you remember, so I'm going to recap what the perceptron is, and so let's see if we have this kind of, say, I mentioned this one is so important to understand visually. So what perceptron does, here we have a constant, or we call it bias, and from here we do linear combinations like plus. This here we do linear combinations, and at this moment we use sign functions, whether the values inside sign is positive or negative. We're gonna say this one is +1 or in this case is -1. I mean, here is sometimes if you use so later on we're gonna replace this one to sigmoid functions, or in that case it probably is 1 and 0s, but let me just, so in sign functions, I guess it will be if that's positive, it's going to be the +1. If negative, it's -1. That's what. So that's a linear combination with nonlinear activations. In this case, I use sign functions to represent the perceptron. In the mathematical expressions, we can write it this way. Or X is like column vectors. And this one is omega naught plus omega transpose X. So omega transpose X is equal to X transpose omega. So either way is fine. And here we have the equations. Like this one is, if you set this one is equal to 0s, this is the how do I say, classification boundary, right? Or decision boundary. Let me see. So it's this again from here we can say that perceptron is one of the linear classifiers, as you can see. Now I want to think about the perceptron in here in geometric sense. And we know that this one represented like that, and this one is when the values inside this is nonlinear activation functions. In perceptron case, again, it will be the sign function. And so let's say this one is 1 plus equal to 0s, and we know that this one is omega transpose X equal to 0s, and omegas and these are the orthogonal. So omega is vector is -2. So if you write it that way, this one is the vector of omega, and as you can see there, these two are orthogonal. Okay, so omega has some the direction informations. It's orthogonal or perpendicular to the linear classification boundaries, as you can see here. So that's how we do. And let's check. So now we know that this one is classifiers. Let's see, suppose we have new input data points, and I want to predict what kind of class that belongs to. So what we can do is just, let's here -1 and 2. So I can compute it 1, and here is -3, and this one is -4. If we do summations, it's -6. Since this, and now we have sine function, since it's negative, it will be -1. So it's here, we know that it's like -1 class, and of course you know that this one is +1 class, and this one is same as, we know that the omega is in this direction, so on over here it will be positive, and on the opposite side it will be negative. Just everything is, I think it makes sense. So from this perceptron, we can tell any given new input data set, we can tell whether this will be is a positive or negative. So we done with the binary classification problems. And I want you to think about this one, and these are equivalent, just different representation. This one is the shape of, we have neurons and like linear combination with nonlinear activations, and this one is the same informations we differently represented in the geometrical sense. And this one is more like, so I use here, say if these are z, the argument of the linear equation function of g, if that g value is positive, y is class is +1. If this is negative, it's -1. So what we did is, it's again, it's a linear classifier, and it's a binary classification problems, as you can see from these two. And let's know, so far is we did in two-dimensional space. I want to increase, say, m-dimensional space. So I want to generalize it from this part, or we can just, all we need to do is just increase the number of neurons, right, unit. So that is how we do. And we, at this point, is like we do sine functions. Over here, it's n-dimensional space. I'm not able to draw or visualize it, but as you just think about the column vectors like this, right? So that's the corresponding mathematical or vector or matrix or vector representations. So that's what we did. I just review or recap the perceptron is. Now I want to keep going to develop what the multi-layer perceptron. So in the perceptron, the neurons compute weighted sum of their inputs, right? So it's the same as omega I xi. We do summations, and from here, let me see. When you do neuron is, so I'm at this moment, neuron is activated or fired when the summation is positive, which means, so if this one is here, I mean in this case, the activation function I'm using like that. Instead of sine functions, we can do, here is zeros and 1. I mean, this is shifted and scaled, so it's pretty much the same. So in that case, it's not sine function, it's a kind of, it's a step function. Now let me see. Now I'm using step function. It doesn't have to be sine functions. So in this case, if that's a negative, so y is equal to 0. That means it's disconnected. And if that's positive values, it will be 1. So that's how we understand these things inside. And here you can use step functions instead of sine functions. I mean, either function is fine. And I mean, this is so far it's good for the perceptron, but the problem is the step functions or sine function is not differentiable. So sometimes I think about it. So if we need when you do the optimization problems, most likely we're gonna use a gradient descent. In that case, we have to take the derivatives of the functions or in the nonlinear functions. But in this case, if we decide to use a sine or step functions, we cannot take the derivative. So this is not good. So that's a weak point of the perceptron. And another one is that one neuron is maybe it's not enough. So one neuron means if you have like this, they represent one hyperplanes. So let's move on to, let's talk about the second case. There are some famous problems, we call it XOR problem. And if the X and Y if you can think of just value of one, or this is Boolean values, or true and positive. If you do take XOR operations, I mean these are zeros, and if you do 1, so in that case, in this kind of lookup tables, what you can do, if these two values are different, it's going to produce 1. If these values are those two values are the same, it's going to produce zeros. Okay, so if I say write it in the coordinate in x1, in x2, or like here, and either here is these two values are different, then it's 1. This is 1 and zeros. And suppose, or you can think of these are the positive and the negative, it doesn't matter. And if we have the training data set, it's a discrete, distributed, or located like that, and say the question is, how do I divide it using the binary classification or perceptron? So if the single lines, I cannot. So to separate these, there's two ways. The first thing is probably I will do like nonlinear classifications, or it's pretty much the same, similar things, but I can think of two lines or two linear classifiers, right? So we know that single neuron represent, or single layer represent one linear classification boundaries. So so the idea is, the motivation is that even for this one is, it's not a complicated, it's looks very simple, this XOR problems. We have only 4 points, and in these problems, even the perceptron is not able to solve even these simple problems. So that was the motivations. So in that case, instead of having one neuron, now we want to add, because in this case, at least we know that we need 2 layers or 2 hyperplanes. So this one is probably, it's going to produce, so we have, how do I say, zeros and 1 and 2, and zeros and 1 and 2. These values probably for the first, and this one is second. So this one will generate this line, and this guy is gonna generate the second one, right? So if the data points is not linearly separable, in that case, we can think of more straight lines or the hyperplanes. In that case, it's same as multi-layer perceptron. So I want to combine these two like this. So we have, because these are the same inputs, but different parameters or different weights. So I can draw like this. Okay. I just simply combined. So in this case, now we know that since we have two, so it's represent two hyperplanes. And another problem or the issues or weak point that we have is that since we have the step or sine functions, it's not so linearly, it's not a differential group. So in that case, we know that the sine step functions is like we can introduce logistic functions or sigmoid functions. It looks like almost same as the step functions. A good thing is it's a differential group. So only thing is that I just changed these sigmoid functions into, okay. And one thing that I want to mention here is this one, even though we have nonlinear activation functions, in this case we happen to use sigmoid functions, this one still represent linear classifier, because the linearities come, the boundaries coming from these are the weight over here, not from this side. Okay, I mean, again, in multi-layer perceptron, we have nonlinear activation functions in it, but it's still linear classifiers. That's what I want to emphasize. And we don't have to use sigmoid functions. We have a lot of different activation functions, hyperbolics, and this one, let me see. This one is sigmoid, and this one is another one is, this one is from -1 plus 1, have hyperbolic tangent, and if we take the derivatives, it will be like this. And another one is rectified linear unit. We call it ReLU functions, and I think this one is nowadays the most famous one and widely used. And this one is, if that's negative, the values are zeros. If it's positive, it will be this y is equal to x. So that's the nonlinear activation functions there. But I mean, here in this slide, what the purpose of this slide is, I'm saying doesn't have to be only one nonlinear activation function. There are many different types, and these are the common activation functions. And for the ReLUs, the rectified linear units, I'm going to discuss later in details, right? And in TensorFlow, of course, it's the only thing we can just is the functions, our activation functions are embedded, so we just make use of them. That's good enough. Now from here we do linear combinations with the nonlinear, or in this case the sigmoid functions. Now in a compact representations, I can combine them together. I mean, these are the same. And by just looking at here, you have to visualize in here x of 1 and x of 2. You have two hyperplanes from these omegas. So maybe these are the inputs, and the first layers. Single layer is not enough to be able to represent complex relations between the input and outputs. So in that case, we can add another layers, second layers, and there will be the outputs. So from these, it's input and the neurons, and outputs. From these, there will be, I mean, these values are the output of the input layers, but by looking at from this perspective, it will be the inputs to this layer. So the first layer, it will be the output of the first block, but the first layer is at the same time it will be the input for this second block. So you can think of this one will be another layers. Okay, so from here we do outputs. So in summary, multi-layer perceptron, it's the same as here the input, and we call it features because it's a nonlinear to do the linear combinations with the nonlinear functions, and we can treat it this one. The feature is as another input for the here. This one is another features, and the outputs will do something on these features. So we call it, this one is features of features. So we have inputs and the features and the features and outputs. Or we can think of as a nonlinear mappings of nonlinear mappings. That's how we interpret of the artificial neural net. Okay. So from here is to represent the dimension of the input space or dimension of features, and here is number of mappings or number of the mapping of features like that. So if we have many layers, that means we do a lot of mappings several times. So that means each layers we have, since we have nonlinear activation functions, and we can represent the complex relationships. And if we have increased the number of neurons, in that case, that means I can represent higher dimensions with many classifiers, linear classifiers. That's what the way that you're supposed to look at the artificial neural net or multi-layer perceptrons. Another perspective that I want you guys to choose is ANN as a kernel learnings, and what the kernel meaning is, I'm going to explain in the following slide. I don't think I explained what the linear classification, nonlinear classification problems, and I mean just think about the linear. This one is we cannot classify with linear hyperplanes like that. Probably this one is proper way to classifications. And just looking at the video clips. Now I do increase dimension to the higher. Oh, sorry. Let me. Now this is not linearly separable, but if you do like this, now its data is distributed in 3D space instead of 2D space, and in that case, it's linearly separable, like with these hyperplanes. So we can find these hyperplanes using the linear classifications in 3D space. Once we have that, now I'm mapping to the original space. Now, as you're looking at here, it's a nonlinear classifier. Okay. So nonlinear classification is I'm using still it's a linear. I'm using linear classifications, but from nonlinearly distributed fit data set, I'm gonna use some kind of kernel functions to make it linearly separable in higher dimensions. I did not, so here this I call it kernels. kernels. So if I summarize it, if the data set is not linearly separable, and in other words, it's non-linearly distributed, and of course, using the linear classifications, we cannot separate them, we cannot divide. And the idea is that if you are able to, I'm not talking about how to find the right kernels, but say we found it, or some of the good kernel is given to us. So using that to remap all the data points into the higher dimensions, and in the higher dimensions, let's suppose that the data is linearly separable. Now it's a linear classification problems in the higher dimensions. Then we know that how to do using the linear classifications. It'll be logistic regressions or SVM or even the perceptron. We can find it, and once we have that, it's a linearly separable case, and the linear boundaries, if you remap to the original space like this, then it's going to be like, but it looks like this is nonlinear classifiers in 2D space. That's how we solve nonlinear classification problems. So the key thing is here, how do you find the kernel functions? So let's see neuron again. We can represent these neurons as follows. And this one is, just use, this one is bias and weight. And so this is the same as like that. So we do that, this one is vectors, and we do vector multiplications or transpose it, and we add bias, and is followed by the, say it's a sigmoid functions or any kind of nonlinear functions, and we can get Y. So that's perceptron. For XOR problems, the main weakness of linear pre-train is lack of capacities. For classifications, the data has to be linearly separable. In this case, it's not. In that case, let's think about, we're gonna do pre-processing to data to make these two populations or data set linearly separable. And let's see, I'm thinking of this. So say this is XU and XV. I'm going to define the kernel functions in here in 2D and 3D. And I'm going to do these multiplications. And we know that these are either zeros or one. So if I do, there will be either one or zeros. Right? So in each data point, if any of them has zeros, all of them are zeros. And if both of them are one, and the third values will be the +1. So this one is we did mappings to higher dimensions. And this is one of the examples. Now it's looks like now in the higher dimensional space, as you can see, it's linearly separable like that. Okay, so the kernel is, we want to capture, say we want to get linear patterns in the data set, and we discuss linear regressions and linear classifications. And in many cases, the linear models is either linear regressions or classification problem is not rich enough. The good thing is, by mapping to the data set to the higher dimensions, whether it exists the linear patterns, it always exists. Then apply the linear models in the feature space. Okay? So the kernel is make the linear models works in the nonlinear settings. That's why you find in the nonlinear patterns, it's really important or critical to find right kernels to do that. So now I want to combine the kernels and neurons or perceptron or linear classifier. So what I mean is that in X as an input, I will do kernel first. I will do pre-processing. Then in that case, at this moment, we know that it's a linearly separable. So we can do perceptron. So the only thing is that I just add the kernels right before the perceptron, between the input and perceptron. And this one is just any, I mean, it will be some functions, right? What we know is a neuron is, we can find some kind of functions or relationship between input and outputs. So good thing is here in the machine learnings, in the feature engineers, it's really important to find the right kernels in that, so that it's in the higher dimensions to make it the data set is linearly separable. But here, what I want to do, just looking at these two, I want these linear mappings or kernels, I want to replace it by another neurons, because we learned that from the previous slides is that there's neurons can represent any kind of the functions and relationship between input and outputs. So these represent the kernels. We don't know what the omegas, we don't know what the B is, but these are the kernels. Okay, so just think about these two. Now just looking at here. Now what we did is, now this one is multi-layer perceptron. Now you have inputs and the first layers and the second layers and the outputs. So this kind of, we can generalize multi-layer perceptron, and in these parts you can think of as a kernels, and from here you can think of it as linear classifier. This one is nonlinear, maybe kernel or mappings. Okay, so this one is the second perspective that I want you to think of. And here as a nonlinear mappings, or you can think of it as a pre-processing of the inputs to make it as a linearly separable. And in later part will be acting as classifiers. And good thing about this framework is that these the values we're going to train, or we're going to learn from data. If you learn it from the data set, that means we learn classifiers. At the same time, we're gonna learn the kernel functions as well, because we're gonna learn all the bias and weights from the data set. So instead of user defining what kind of kernel is good for these problems, now user is gonna do not anything, but we're gonna ask the neural net or multi-layer perceptron to think of it from the data set, or to learn even the kernel functions and the linear classifiers at the same time from the data set. Okay. So in this case, we don't, input, and these are the features and another features. So if you by user defined kernels, that means we do feature engineering by domain expert. But in this neural net, it's a feature learning process plus classifiers as well. So the big difference, machine learnings and the deep learnings, and machine learnings by the domain expert, we have to determine or decide what kind of the features are important. But in deep learning field, we're gonna ask the neural net to try to figure it out by itself what kind of best features from the data, just from the data. So for summaries, and you can think of as a multi-layer perceptron or artificial neural net as universal function approximator or universal function classifiers. So these are the kind of general the structures. We have inputs and hidden layers and the outputs. We can add more hidden layers in between. And these are the omegas. And with the various special structures, and it's parameterized. Omegas and weights and bias, those are the parameters values, and we need to figure it out from the data. So in the artificial neural net, it's nothing but we have inputs and outputs, and these are the neural net parameterized with all the weights and bias. So let's talk about the big picture of artificial neural net. And the general purpose is that we want to find universal function approximator between the input and outputs. In many cases, the relation is going to be the complex and nonlinear behaviors between them. And how do you figure it out? How do you do? Is that we want to do linear combinations with linear connected networks to represent the complex behaviors. And in order to handle the nonlinear behaviors, we need embedded nonlinear activation functions, but we want to have very simple version of that. So it's a very simple nonlinear neurons inside. And if you have, say this one is, I just rotated, this is inputs and the outputs. And here is linear combinations with nonlinear activation functions. And if this is inputs, now from this part, and there's two parts, and now you know that this one is features, and we do feature learnings, and the later part will be the linear classifiers. That's artificial neural net all about. That's all about the artificial neural net. And what we need to do is we need to find all the weights and bias for between layers. So what about this? So now this is deep artificial neural net, which means the number of layers is very deep. Okay. So that means here, instead of having one corners, you have many corner functions. So that means we have higher capabilities or ability to have, you have capability of to represent very complicated the feature behaviors. Okay, that's how the name deep is coming from. So good thing is we have higher chance to get the good features already for the classifications, but on downside we have many unknown parameters, and those are might be different. Those are different. we have many unknown parameters that we need to solve or we need to figure it out, say from the optimization solvers, right? So we have many unknown parameters to solve or to find out. Because of that, we need a lot of data set. So it's related to big data set. Because of that, we need a lot of computations, right? Higher computation requirement. That's why we need probably GPU to compute it, yes. So all these things are related to, and how we're gonna to figure out all the weights and bias. I mean, we're gonna use the gradient descent method. Gradient descent method. Descent. Okay. And let me now let's looking at the parameters means weight and bias. So examples, if you have linear, let's think about the linear classifier first. And suppose we have, I mean, this kind of thing is, it's a binary classification problems. I want to separate these two classes of data by dividing them with a line. I mean, here, I mean, these are, say, is class 1 and these are class 2. I cannot divide it like this, right? So it's not linearly separable, right? So it's a nonlinear classification problems. So let me see. I want to use this problem using artificial neural net or MLP, multi-layer perceptron. And since this is, say, x of 1 and x of 2, and these are and we have the bias terms. And here, at least I need probably 2. I think that's the minimum. So I add from these, I will get 1 layers. I don't know which one is that, but from these combinations, probably I get another lines. Okay. Then I will do from here to here, I will do another classifications. So if we do hidden, that's one way in looking at the neural net. Another one is you can think of this one as another corners, and the hidden layers learns representation, so data gets linearly separable, and probably this will be the output. And if you're looking at here, let me see. So this is the output, and this is the inputs. And suppose we learn all the weights and bias, and the corners we can do here. If you use that, because we here is, it will be the some kind of mappings here, and this one, the nonlinear boundaries is related to linear classifiers. That's what's happening inside. That's what's happening inside. We kind of distort the space, the nonlinear space, to make it linearly separable. And in that linearly separable space, we can easily, or neural net easily can figure out the linear classifiers. That's how things are happening inside. Let's take a look at more concrete examples for that. And I want to take a look at the logistic regression problems to explain it. And as you can see, if you have this kind of linearly separable data set, and probably this one is a linear boundaries, and you can represent it like this. Okay, so omega, I mean here, this one is bias, and these are the weights. Now I'm just, this one is omega naught, and I'm gonna change the notations. Say this the B, because in artificial neural net communities they use B to notate the bias, and these are the same. I mean here this same as like that. Now this one is the right notations, but I'm not gonna, so just for simplicity, I'm not gonna indicate the bias units. I'm just gonna say like this, okay? So here have two inputs and one output. And the omega 1 right here is represented the line in two-dimensional space. Another one that you have to know is that one-hot encodings. It's a conventional practice for multi-class classification problems, and in this case, it's binary classification problems. So, if we do that, if the y is equal to either 1 or zeros, right, to represent the different classes, and by doing one-hot encodings, I want to add 2 neurons in the output place. And what I can say is that I will say in class, say in class 1, it will be 0, 1. That's for the class 1. For class 2, it will be 1 and zeros. So that's how we do for one-hot encodings. So in that case, we have 2 inputs, and since it's binary classifications, the output is 2. So for multi-class classification problems, if we, I suppose we have 10 classes, by doing, let's say it's 4, then for the multi-class classification problems using one-hot encodings, the output, y, we have 4 neurons. In the first class, it will be 1 and zeros. In the second class, all of them are zeros except the second. And that's how we encoding things. So we're gonna use one-hot encoding a lot. So please make sure you understand why we are doing one-hot encodings for multi-class classification problems. There is a lot of good advantages. So probably you will have a chance to see the advantage for the later on for the NNIST data set examples. So in this case,
sorry, I just, why do we have a column of 0 first? I've misunderstood.
Column is equal to zeros.
No, the column of zeros, the first one.
No, oh, this one.
It's not columns. Oh, okay, so, it's not zeros. Okay.
Unit.
Sorry. Yeah. Okay.
So
sorry.
So for one-hot encoding, since we have this one is now, you can have this one represent, say, one of the lines, and this one represent another lines. That's why we here in here we have 2 lines. Okay, since we decide to have one-hot encodings, we have here and these we have 2 hyperplanes. But if this one is 1 and the other should be zeros, right? And zeros and the 1 is close to 0 or close to 1. So there's 2 classifiers, but it had both those 2 classifiers are pretty much the same because both of them are. This is because we have binary classification problems. Now let's think about more interesting case. Now, say the data is not linearly separable, and it's non-linearly distributed data. So I intentionally generated data set like that. Okay. And as you can see, the right answer probably, like this probably is good nonlinear classifiers. And I want to do nonlinear classifications using ANN or multi-layer perceptron. So as you can see, we have two-dimensional space. Okay, and I'm to say here, I need here from these, I'll have one line, and from these I'll get another lines. Okay, then I add one more lines, and I don't want to include the bias, because then this one will be the, okay, so we have two inputs, two hidden layers, and two output neurons. So let's see from here. And the original data set is from, let's say, from these are the values. And if you look at here, we have sigmoid functions. So the z values should be from the values from 0 to 1. 0 to 1. So if we have, we say we're done with training, and instead of plotting the x of 1 and x of 2 in the original space, I want to plot z values in z space. Then this one is the first thing. So I plotted the data set in z space. And the first thing that you have to see is that from 0 to 1 and 0 to 1, because we have sigmoid functions. Okay. And you can think of this layer as a corner functions. And from now, as you can see in this space, it looks like almost linearly separable, because all the blue on the red dot is located here, and the blue one is located here. So what we can, if we plot it, the weights over here, and we have one-hot encodings, we have two lines. Both of them are pretty much the same. That's how we figured it out. So how do I say? Here is linear classifier, and this part is acting as corners. Good. Now the next question is, I want to know, because eventually we will get some weights like that, right? And I want to know what kind of the hyperplanes in the original space. So here into original space, I got one line. I'm not sure which one is, say, this one, and the other one is like that. So that's what. So what I'm saying is that the original problem was nonlinearly distributed. Think about the XOR problems, and since I fixed the structures like this, that means I can use two hyperplanes or two straight lines, and this one is the optimal one to minimize the number of misclassified data points. I hope you understand this. This one is the very critical one to understand what's going on inside artificial neural net. And this one is this part. It's from using the corner functions, it's acting as a corners, and from the nonlinear distributed data set, using the corners, it make it linearly separable, and followed by just simple linear classifiers. Now let's think about even, so here, if we have this kind of, if I ask you to design your artificial neural net or multi-layer perceptron, and how many neurons that you, this is inputs, and it's so of course we have this, and these are the fixed, and this binary classification problem, so we have 100 encodings, so 2 neurons and 3, and probably just don't include this, so it's 2. And how many neuron that you think is required in that case? What's the minimum number of neurons that you believe you need to set? Okay. The other way that I can say is, how many do you think, how many lines that you need to separate?
More, 4?
4, right? So probably like that. Probably. That's why I intentionally include 4 neurons in hidden layer. So the reason why that I'm doing this is that because in the real case, data is gonna be given. So now you have to design the structure of neural net by yourself. And I want you guys to have some kind of insight, how many layers that you need, how many neurons for each layer that you need to put it. Right? From these directions, it will do how many, probably based on the complexity of the relationship between the input and outputs, how many corners that you need, how many features that you need. And this one is the number of neurons, is that how like the data set is non-linearly behave. It really depends on the complexity of your data distribute the behaviors. So it's not like exactly it's matched, but I want you guys to have at least some kind of insight on it. The number of layers and number of neurons units. So I repeat it, and if you're just looking at the Jupyter notebooks, probably you will see how I implement it. And it turns out that I plotted the omegas, and this will be what the ANN suggests. It's different from what I expected, but it seems like it's okay, right? So these are here's these misclassified data points, but this one. So I thought there would be this will probably be what the ANS recommend or come up with, but it's a different. But I kind of convinced that these lines are also, I think, it's fine. Okay. Any questions? And now I'm going to move on to how do you find weights and bias. So the title is training. And again, we want to estimate weights and bias for the MLP from the training data set. And as an optimization perspective, so for optimization, I mentioned several times that we need to figure it out or identify 3 key components. The first thing is what is the objective functions, and it's going to be the decision variables or unknown omegas, and will be the constraint. So mathematical expression is probably this one is the objective functions with omegas. In general, we don't have any constraint on weights and bias, so it will be unconstrained problems in general case. So that's but the constraint is that they have very unique structures like that. You have all the connections. It's layer by layers. That's the unique structure. Is that's something that I need to predefine. So that's the, and I can convert it to these problems into these unconstrained optimization problems and to figure it out, to verify all the weights and bias to minimize the objective functions that I'm going to define. So objective functions. So again, I can maximize, I can minimize. So I'm gonna keep that as minimization problems. So it's equivalently, I'm gonna say it's loss functions. I want to minimize loss. What kind of loss will be given x for each data point? Y is either true value or true labels. If this regression problems, it will be the values, and for classification problems, it will be the labels. And this one is represented by multi-layer perceptron. So it will be y hat. And predictive values, and there will be some errors between them. I will define it loss. So I want to minimize that for entire data set. So for example, for the regression problems in that case, probably the square loss like that will be the common. For classifications, like I mentioned several times, this logistic regressions problem or the softmax, it will be I'm gonna use the cross entropy things. I hope you guys remember this. So in the same, I mean, in these kind of structures, since we know the x and we know the outputs, and by looking at the, I mean, computing the forward, and I can compute the y estimated values, and I can make comparison of these two. For in many cases, for the regression problems, I will do squared, and for classifications, I will think about the cross entropy to minimize that. How do you solve the optimization problems? I think the only thing that we learn from is the gradient descent, and this is the most generic and powerful way. So like negative gradient points is down here to the cost function because we are trying to minimize the cost functions. And these are the, in many cases, it will be the multivariate. So it will be the gradient with respect to omegas. Omega is all the unknown parameters. In terms of neural net, it will be weight and bias. And the R pi is running late or rate or the step size. So let me see. And let me think about, say, if we have, so don't worry about the bias and how many weights here. If we have 3 neurons and 2 neurons, how many weights? In other words, how many lines that you need to connect?
6.
You get, I mean, right? So probably I will say, I mean, just, but I just for simplicity, I'm gonna exclude bias, but so here we need 6 weights, and suppose we have another 3, then how many lines here?
12.
Another 6, right? So in total we have 12, probably I will say, unknown variables. And think about, say your input is 10, and somehow I decide 100 neurons in the first hidden layers and another 100, and I have the 10 classification problems. Then how many weights in total? How many weights? Now we have 1,000, 10,000. So that's maybe. That's, I mean, for even these the simpler models, these are the number of unknown variables that we need to find. We need to figure it out using the gradient descent. That's a lot. I mean, this is extremely small networks. So that's, I mean, the reason why that I'm mentioning this is think about the complexity of neural net, or for, even though, I mean, this is just simple models, that is, these are the number of unknown parameters that we need to estimate it. So it's kind of exponentially explode. So it's a lot of unknown parameters that we need to figure it out. So for gradients, so the idea is that for gradient, it's because say we have, suppose we have 1,000 omegas, and we can compute the x and y. Suppose we have 1,000 data points, and we can compute loss omega I. If that's for like that, in theory, we're gonna have 1,000 these gradient descent equations or updates for each iterations. For each iteration, so because this is iterative way, so we have just the first iterations, we have omegas. In the first iterations, it's randomly assigned. I will do 4 propagations to compute the loss, say true values. And for entire omega, say so 1,000, we have to do all like this for each lines. And whether we can compute it, this is just whether the slope is positive or negative, and that will give us the idea that in the next iterations whether we need to increase that rates or decrease for each update. I mean, in theory it's possible, but the problem is it requires too many computations. That's the problem. So there's the information that we did not use so far is that in the structure wise, it's layer by layers. We do not use that information to compute the gradient. So the structure constraint is that it's a composition of the functions and chain rules and dynamic programs that we are able to use